so unlike the previous method, which is restricted to one dimension, the transfer matrix method is something that can be generalized to more than one dimension. But in addition to this, I will show you now that the recursion method is actually something that you can use only in very particular situations. It's not something that you can pretend to use for general models. Because, for example, when we consider the recursion method in one dimension, as we have done previous time, suppose that instead of considering the recursion method applied for an easy model in one dimension with a Hamiltonian, with this Hamiltonian, we include a magnetic field that breaks explicitly the symmetry. Okay? So now, in this case, you see that if I can play the same game as that I played last time. So sum up explicitly over the first, sigma n minus 1 equal to plus n minus 1, e to the minus beta plus beta sigma 1 sigma 2 plus beta, this is beta j plus beta h sigma 1, etc., 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 and then I can sum over the last spin. E to the beta j sigma n minus 1 sigma n minus, oh, there should be a minus here, minus h sigma n. Now you see that when I perform this summation here, what I get is that this is equal to 2 the cosine hyperbolic of beta j sigma n minus 1 minus h, right? And now I have a problem. While before I was dealing with an even function here, and therefore the result did not depend on sigma n minus 1, and that's why I could write down a recursion relation. Now it depends explicitly on sigma n minus 1. In other words, I did something and I obtained nothing because it's more complicated than what I started with. This tells you that the recursion method is great, it's very, very simple, but it's not something general that you can apply to all kinds of problems. And therefore, if we want to solve a general problem, including this problem with a magnetic field, we have to resort to some other formalism. Okay? So, this other formalism is the transfer matrix method. So suppose that now we will consider, so this is called a prelude. Prelude. Why am I making mistakes all the time today? Prelude. Okay? So now, the real lecture starts here. Let us consider now an easy model in one dimension with periodic boundary condition. Okay? I'm changing the boundary conditions. You will see why in a second. I will explain it. Minus h sum over I from 1 to n sigma I. Now, I want to have periodic boundary conditions which means that sigma, actually, this should be not 1 but n. Sigma n plus 1 should be equal to sigma 1. Okay? This is what periodic boundary conditions means. Now, periodic boundary conditions means essentially that I'm dealing with an easy model that is defined on a circle. Okay? Nothing else but a circle. And now the question is, okay, so what do I do with this easy model now? Well, I want to compute the partition function, so let us write the partition function is going to be sum over sigma 1 equal to plus or minus 1, etc., sum over sigma n equal to plus or minus 1 of e to the beta j sigma 1 sigma 2, etc., e to the beta h sigma 1, etc. Okay? Now, this is equal to what? I can now rewrite, I want to rewrite this expression, this sum, in a more symmetric form. Essentially, I want to rewrite the sum of a product of exponentials in which each exponential has the same expression, as the same exponent. So how do I do that? Well, I write this as sum over sigma 1 equal to plus or minus 1, sum over sigma n equal to plus or minus 1 of what? Of e to the beta j sigma 1 sigma 2 plus beta h sigma 1 plus sigma 2 over 2 times, well, let's write it down here, exponent of beta j sigma 2 sigma 3 plus beta h sigma 2 plus sigma 3 over 2, etc., e to the beta j sigma n sigma 1 plus beta h sigma 1 plus sigma n divided by 2. So you see, what I wrote here is exactly what was written in the previous slide. Because you see, here, half of the beta h sigma 2 is put here in this first exponent. The other half is put here. I have all the products, sigma 1, sigma 2, sigma 2, sigma 3. Now you might say, where is the other half of sigma 1 gone? It's gone in the last term because I had the periodic boundary conditions. Okay, so everything is fitting. Now this, I can rewrite it as follows. I can define the function v sigma prime as exponential of beta j sigma prime plus beta h over 2 sigma plus sigma prime. Okay? And if I define this function, so definition is the mathematicians use 3 lines. If I define this, let's put it in a. So if I define this, then I can rewrite my partition function, as you see above, as the sum over sigma 1 equal to plus and minus 1 sum over sigma n equal to plus and minus 1 of v sigma 1 sigma 2 v sigma 2 sigma 3 etc. v sigma n sigma 1, right? Correct? You all agree. Great. So now let us look at what we just wrote here. And let us remember a few things about matrices. Reminder. If I have two matrices, then in components the product A times B ij is equal to the sum over k A ik B kj, right? And if I want to write, for example, the trace of the matrix A times A times A times blah 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 A n times, then this is equal to the sum over, I don't know, I1 sum over all the way to In A, I1, I2, A, I2, I3, etc., A, In, I1, and that's it. Okay? So this is the trace of this matrix to the power n. Where do you see that it's a trace? Because the last and the first and the last indices are equal, and I'm summing over the first and last index. Okay? Clear? So now let's look at the expression that I have here. You see that I have the first and the last index that are equal because of periodic boundary conditions. Now this function here, sigma, can take only discrete values. So I can think of it as the index of a matrix, right? That can have two values, plus and minus 1. So if I think of this as the index of a matrix, then it's clear that, so my matrix V is going to be in components, is going to have the expression E to the beta j plus beta h, e to the minus beta j, e to the minus beta j, the e to the minus beta j minus beta h,
plus beta j.
Plus beta j, that's right, plus beta j minus beta h. And now you see that if I do this, then my partition function z, according to what I wrote before, can be just written as the trace of v to the power n. Okay? So V is what is called the transfer matrix. Why the transfer matrix? Why the transfer matrix? It's called the transfer matrix because essentially it connects configurations of different sites. So it's essentially the matrix that tells you how to connect the configuration of site 1 with the site 2, which you have two possibilities for site 1, two possibilities of site 2, and therefore you have a transfer matrix, which is a 2 by 2 matrix, right? So it just gives you the weight for the various possible different configurations of these two sites. Now, there is one thing that you might ask me. So this is true for periodic boundary conditions. So for periodic boundary conditions, you get transfer matrix. You get that the partition function is the trace of v to the power n. What happens for non-periodic boundary conditions? What about if I fix, for example, the direction of the spin in the two boundaries? Okay, I don't consider periodic boundary conditions. Now, in that case, so this is periodic boundary conditions. If you don't have periodic boundary conditions, but for example you fix the boundaries, then you can generalize this expression to have something like this. Boundary 1, v to the end, boundary 2, where these two states, 1 and 2, are just two 2 by 2 vectors that represent what is the boundary condition that you put on site 1 and the boundary condition that you put on the last site. Okay? So this would be the generalization, but we are going to deal with periodic boundary conditions because in any case it should not matter unless you are interested in finite size systems, right? Now, Why is this way of writing the partition function interesting or useful? Well, it's interesting because you can easily now express this partition function in terms of the eigenvalues of the transfer matrix. If you're able to diagonalize this transfer matrix, then it's evident that you can write Z in terms of the eigenvalues. Why? Because suppose that you find a matrix, a rotation, that diagonalizes the transfer matrix. So that is such that u to the minus 1 VU sets the transfer matrix into diagonal form. So lambda plus 0, 0, lambda minus. Then it is evident that Z is going to be equal to trace of V times V times V n times, right? But this is equal to the trace of V times U to the minus 1 times V times U to the minus 1 times V, etc., times U to the minus 1 times V, right? Because U times U to the minus 1 is 1, is the identity. Okay? So this is the identity. And therefore this is equal to, I can write it as trace of U to the minus 1, V, U to the minus 1, etc., V, blah, 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 U to the minus 1, V. I put another U to the minus 1 here in front. And now I use the cyclic property of the trace that tells me that, for example, I can take this guy and this guy here and put it and throw it at the end, and the trace is going to remain invariant. So therefore, I get, if I do this, I get that this is equal to a trace of U to the minus 1, U, no, not U, V, U to the minus 1, V, U, blah, 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 n times. So this is equal to trace of D to the power n, right? Where D is the diagonal form of the matrix V. But trace of D to the power n is trivial. This is lambda plus to the power n plus lambda minus to the power n. Okay? So all of this tells you, therefore, don't get too excited about this, okay? Because in principle it tells you that if you want to solve a problem in statistical mechanics for discrete, for this kind of discrete problems, it's just enough to find the transfer matrix and to be able to diagonalize the transfer matrix. And that's it. You're done. You solved your problem. Most importantly, and this is really something impressive, notice one thing, that typically, so when you have a matrix like this one, so let's go to, no, actually, let me say this at the end. Let us do now the exercise of finding the solution, okay, for our easy model using this technique. So in order to find the solution, we just have to find what is lambda plus and lambda minus. Okay, the two eigenvalues of this matrix V. And in order to find the two eigenvalues, we have to solve the equation determinant of V minus lambda times the identity equal to 0. Okay? Now, means just do it. Okay? So if you do this calculation, you're all able to do this calculation, right? You did it 10,000 times. You know, my advisor, back when I was a PhD student, was not able to do any one of my advisors was not able to do any calculation. But he knew how to diagonalize a 2 by 2 matrix. That's the only thing he knew how to do. Okay, so that's the maximum achievement in terms of calculations, and he was a very famous physicist, actually. So that tells you that calculations are important, but not that important. Anyway, so if you...
Sorry, is there a chance of degeneracy in this case?
Well, let's write down the result, and then we decide if there is a chance of degeneracy or not, right? So, lambda plus and minus, if you solve that, you're going to get a quadratic equation, so you're going to get 2 eigenvalues, and then the 2 eigenvalues are these ones. Do beta j gosh squared minus 2 sinh 2 beta j. Well, in order to get the degeneracy, you have to set the discriminant here equal to 0, right? I don't see any, well, it might be that for a fixed j you find an h such that, but I don't see any simple way to do it. Anyway, so these are the two things, and notice that lambda plus is greater in absolute value than lambda minus. This is something that you can check yourself. Okay? So now, the partition function z turns out to be equal to lambda plus to the n plus lambda minus to the n. Okay? Now, let's see something. Let's set h equals 0. We want to check ourselves, right? We don't know if the calculation is correct. We set h equals 0. So if we set h equals 0, lambda plus minus comes out to be equal to what? E to the beta j plus and minus the square root of e to the 2 beta j minus essentially e to the 2 beta j plus e to the minus 2 beta j, right? Because I'm spelling out what the sine hyperbolic is. So what I get is e to the beta j plus and minus e to the minus beta j. Okay? So this is equal to 2, well, the plus is the cosine hyperbolic, 2 cosine hyperbolic, the minus is 2 sine hyperbolic. So, okay, so if I want to write down this, what I will get is 2 to the n cosine hyperbolic beta j to the n plus 2 to the n sine hyperbolic beta j to the n for h equals 0. For h not equal to 0 is something else. Okay? Now I want to check myself. So let me compare to what I did with the recursion method. So recursion method with the recursion method, what I got was z equal to 2 to the n cosine hyperbolic of beta j to the power n minus 1. perfectly. It doesn't. I made some mistake in the calculation. Did I?
The boundary condition.
The boundary conditions. That's exactly the point. These two guys are different because of the boundary conditions, because I chose two different boundary conditions. They are exactly the same when are they exactly the same? In the thermodynamic limit. In the thermodynamic limit, they are exactly the same. Because in the thermodynamic limit, this guy wins over this one, right? And therefore you get that, I mean, in the thermodynamic limit, if you compare these two functions, when n is sent to infinity, you will see that they are essentially the same. This -1 goes, and this is equal to that. You see? So this tells you that it's okay to do comparisons, but be careful, because you have to compare results, for example, in a meaningful limit. So in this case, it's the thermodynamic limit. It's okay to have two different results with different boundary conditions. There's no problem about that. Okay? So the reason they are different is because of boundary conditions. Now, there is another important lesson that we get from this, which is the following. Z is, I wrote it up as lambda plus to the n plus lambda minus to the power n. Now, and I told you that one is larger than the other in absolute value, so I could take the largest, lambda plus to the n, and write this as 1 plus lambda minus over lambda plus to the power n. And therefore it's clear that in the limit, in the thermodynamic limit, when n goes to infinity, this is just lambda plus to the power n. Right? Now this tells you something important, that if you really want to are interested in finding the free energy, the log of the partition function in the thermodynamic limit, you don't really need to find all the eigenvalues of Z, of the transfer matrix, but you need to find only the one which is the largest in absolute value. Okay, and that's it, and all the rest will just follow. Now this is important because there are some numerical methods. I'm not really an expert in numerics, so you have to ask other colleagues here, but I know that there are numerical methods to diagonalize matrix that in particular target the largest eigenvalue in absolute value. So you're able to selectively find that largest eigenvalue, which is something that is very, very important. Anyway, so this is the solution, and in particular is the solution for m not equal to, for h not equal to 0. So this tells you that, for example, one thing that you can do with this partition function that we just found is compute the magnetization, df, dh. So I'll give you this exercise to take the transfer matrix that we just wrote and take this derivative and study the limit of beta going to 0, the two usual limits, beta going to 0, beta going to infinity, and see what comes out. Okay? All right.
Sorry, the question that Jesus asked about the degeneracy.
Yes.
Physically, like, the equation can be solved that we can like fine-tune the magnetic field, so the lambda plus and lambda minus will be the same. Because the square.
I think you can. I never thought about it, but I suspect that for any fixed J, you can tune the magnetic field in such a way as to have a degeneracy.
But physically,
What it means, the degeneracy? I don't know. To be honest, I don't know. I don't know. I don't really see.
because in
Well, okay. Let me now show you something, and perhaps you will. What?
The factor by 2.
yeah, it will J by only by
Yeah, of course, but a factor is not physics. You know, a factor according to the Silva units is 1. T is equal to 1. So it's not physics, a factor. Well, it has a physical meaning. We will see it in a second, but it's not such a deep physical meaning, this degeneracy. So let me explain what I mean. So the next thing we will do, which is something that I'm not going to pretend that you know how to use in any case, but it's important for you to know it, is called the quantum to classical correspondence. Now, the quantum to classical correspondence essentially means the following, that there is a correspondence, and it's very precise, and we will make it in a second, between D-1 models in quantum mechanics and D+1 models in classical stat mech. In which sense? Let me explain you. So in the sense that, so the vague answer to in which sense is the following. Whenever you use this correspondence, it means that if you want to compute the partition function, the problem of computing a partition function in a d-dimensional classical statistical mechanics problem is equivalent to the problem of diagonalizing an Hamiltonian in d-1 quantum mechanics. Okay? So you can reduce one problem to the other problem, and vice versa. How does this correspondence work? Well, it works in the following way. Let me try an innovative way to explain this, because people get confused every single year on this. So let us decide that on this side of the word, on the left, we have classical. And on the other side of the word, we have quantum. Okay, so now we have just seen that the partition function z of n guys can be written as the trace of v to the n, sum over sigma 1 equal to plus or minus 1, sigma n equal to plus or minus 1 of v sigma 1, sigma 2, etc., v sigma n, sigma 1. Okay? I could write this in a sort of quantum mechanical notation which adds nothing to what we already know. Writing down this as sum over sigma 1 equal to plus and minus 1, etc., sigma n equal to plus and minus 1 of sigma 1 v sigma 2 v sigma 3, etc., etc., etc. Why can I do this? Because I can define the operator in quantum mechanics V equal to e to the beta j plus times cosine hyperbolic of beta h times the identity plus e to the beta j sine hyperbolic of beta h times sigma z. And you see that if I now define the expectation value of this quantum mechanical operator on the states sigma v sigma prime, where sigma and sigma prime are spin up and spin down, usual spin up and spin down in quantum mechanics, right? Then you get exactly the matrix V sigma sigma prime that we defined before. Okay? So up to now, what I did is what professional physicists call cosmetics. Okay? As if just like when you paint your face or brush your teeth, or I did nothing. Okay? I did absolutely nothing. It's just rewriting things in a different notation. You all agree with me, right? But now, why did I write things in this notation? Because now I remember quantum mechanics. Quantum mechanics, let me use purple for quantum mechanics. So in quantum mechanics, you're taught that if I want to compute, for example, if I'm given an Hamiltonian and I want to compute this amplitude, okay, well, so which is the, for example, this amplitude is the amplitude. I start with the state sigma 1, I time evolve it, and I want to see how much the state survives. Okay? I just want to compute this amplitude here. I can write this as sigma 1 e to the minus I h t divided by n e to the minus I h t divided by n times sigma 1. You agree with me? I can do that. And then I can put what is known as a resolution of the identity in between each exponential, right? You know what is a resolution of the identity? Is a resolution of the identity means that the identity is equal to the sum over sigma of sigma sigma, right? So I don't know, people call it in many different ways, but I put this guy in here and see what comes out. And what comes out is this. I get sum over sigma 1 equal to plus and minus 1. Sum over sigma n equal to plus and minus 1 of sigma, well, let me sum over sigma 1 here. Sigma 1 e to the minus I h t over n, sigma 2, and then times sigma 2 e to the minus I h t over n, sigma 3, etc., etc., etc. Now you see, this expression, which represents an amplitude in quantum mechanics, is very, very similar to this one. There's only one difference, is that this is a unitary operator and this is an Hermitian operator, right? So they represent the same thing, provided I'm sorry, I have to go to the next page, but provided we do the following. Provided we write, if I write V e to the minus a times h, and I compare it to what I had before, a that was equal to e to the minus I h t over n, you see that the two expressions are actually identical formally, up to the fact that I want to identify my I t divided by n with what was a real a. So I perform what is known as a Wick rotation. I pass from real time to imaginary time. Okay? All of this is a game of cosmetics. Okay? It's a beautiful game of cosmetics. So, in other words, what I just told you by this game of cosmetics is, look at this. If I now take this v and rewrite it as e to the minus a times h, I can think of this h as a quantum mechanical Hamiltonian. And diagonalizing v and diagonalizing h is the same problem. Perhaps the quantum mechanical problem that corresponds to h is a problem that I'm able to solve. If I'm able to solve this quantum mechanical problem, then I will be able to solve for the transfer matrix, and I will be able to solve the statistical mechanics problem. You see what I mean? It's a very simple reasoning. All the rest of the analogy with amplitudes, etc., is just to make you see the correspondence between the two formulas. Okay? Great. So now you can ask me, is this really simplifying my life? This quantum to classical correspondence? Yes, it is. It is simplifying it a lot. For example, let me show you. If you consider your one-dimensional easy model, the one we just solved, and you pretend to rewrite your v in this form, then you can ask yourself, what would be h? Okay? Well, h would have the following form: h quantum, let's put it like this, would be equal to minus 1 over a times 1/2 the log of sinus hyperbolic of 2 beta j plus arctangent hyperbolic of e to the minus 2 beta j sigma z. So it's just the Hamiltonian of a single quantum mechanical spin in a magnetic field. Okay? In other words, but this is obvious. If I'm able to diagonalize a single zero-dimensional quantum mechanical spin in magnetic field, then I'm able to solve the one-dimensional classical statistical mechanics problem. Right? Coming to your degeneracy. Here I wrote down this expression for h equal to 0. Right? Now, when I have a spin in a magnetic field, when do I get a degeneracy in the spectrum? When the magnetic field is 0, right? So the physical meaning of that degeneracy that we were discussing before is going to be that for those fine-tuned conditions, you're going to get that the magnetic field that stands in front of the sigma z is going to be equal to 0. I don't have the expression, I didn't do the calculation, but I'm sure that if you do it, you will get it. Now, for the one-dimensional easy model, this is a pretty useless statement because, why would one... we know that we have to diagonalize a 2x2 matrix, and a 2x2 matrix is of course equivalent to a quantum mechanical spin, so it's not a big deal what we just discovered. But this quantum to classical correspondence becomes extremely important in higher dimensions. For example, if I take the two-dimensional easy model on a square lattice, then where here I have n column, n rows, and here I have n columns. Okay, so in this case, you can build up the transfer matrix. You can write your partition function Z as trace of V to the power n. But the matrix V is not a 2 by 2 matrix, because it's going to be the matrix that connects the configurations of different rows. Right? So the index of the matrix is going to be the sigma that corresponds to all the configurations of a row. So how many indices is going to have this matrix? Well, how many configurations does a row have? 2 to the m. So this matrix here is going to be a 2 to the m times 2 to the n matrix. Now you see, the moment you escape from the one-dimensional world where everything was beautiful and simple, you get horrendous matrices that can hardly be solved numerically, because 2 to the m is a huge number if m is some reasonable, I don't know, 20. So you see, life becomes extremely complicated for this kind of problems. Still, for the two-dimensionalism model, if you write your V as e to the minus h a times h, it turns out that your h is equal to is a one-dimensional quantum problem, because we have a two-dimensional classical problem, and this would correspond to d minus one-dimensional quantum. So it's a one-dimensional quantum problem that is just an Ising chain, this one, in a transverse field. This is a quantum mechanical problem, because this guy does not commute with this, you know, the algebra, the angular momentum algebra, but it turns out that is exactly solvable. I'm not going to explain you how. It's just for your information. So this part of the lecture is like what my advisor was. You know, my advisor was calling this kind of parts of lectures Italian opera, because he was not Italian. So he was saying it's like when you go to the Italian opera, you like the music but you don't understand the words. Okay? And he didn't realize that I do understand the words as well, but that's another story. Okay, so this is what my advisor was telling me is Italian opera. So you like the music, but perhaps you don't understand all the details. Okay, but keep it in mind, it's something important. I'm not going to give it to you as an exercise in the final exam if you behave. Okay? Question? No. Okay, so great. All right. So now, given this, let us see another example of this transfer matrix method for the one-dimensional Potts model. Okay. So for the Potts model, we will have, if you go through the derivation we went through to now, you will have that your partition function is sigma 1 equal from 1 to q, etc., sum over sigma n from 1 to q of v sigma 1, sigma 2, v sigma 2, sigma 3, etc., v sigma n, sigma 1. And now our v sigma prime is e to the beta j delta sigma prime, and therefore is a matrix that looks like this. It's e to the beta j in the diagonal, and the outside of the diagonal is always equal to 1. So there is a bunch of 1s everywhere. All right, and it's a Q by Q matrix. So a Q by Q matrix might not be the simplest thing to diagonalize. Well, of course, I mean, you can always do that on a computer, but it turns out that in this particular case, one can do it. So how do you do it? You do it by a recursion method. I will explain it in a second. So suppose that Q is equal to 2, right? A two-state Potts model. Then in this case, you have to compute the eigenvalues of e beta j 1, 1, e to the beta j. So pull x equal to e to the beta j. Then it turns out that the determinant of v minus lambda, the identity, is equal to x minus lambda plus 1 times x minus lambda minus 1. This is something that, of course, JDI. Okay? And then you find that you have two eigenvalues, x equal to lambda minus 1, well, lambda plus and minus 1, right, are the two eigenvalues that you will get in this case. All right, so this is Q equal to 2. What about Q equal to 3? Right?
Yep.
Strange. It's not forecasted. Okay, what about Q equal to 3? For Q equal to 3, your matrix is going to be x1, 1, 1x, 1, 1x, and then your determinant v minus lambda identity is going to get, okay, usual story, JDI, just do it, is going to be equal to x minus lambda plus 2 x minus lambda minus 1 squared. And therefore, you see that you will get x, well, not x, but lambda equal to lambda minus 2, and then two degenerate eigenvalues, which are equal to lambda plus 1. Okay? I hope it's covered. Well, is it lambda? No, it's, sorry, I made a mistake, made a mess here. This is x, and therefore I will get lambda equal to x plus 2, and lambda equal to x minus 1 doubly degenerate. All right, so now, if you're given this, okay, what happens to this determinant for generic Q? What am I going to get? So this is for Q equal to 2, this is for Q equal 3. What am I going to get for generic Q?
X minus lambda plus Q minus 1.
X minus lambda plus Q minus 1 times x minus lambda minus 1 to the power Q minus 1. Right? And therefore, this tells you that in general, And this is something then you can prove by, by induction, for example, if you're interested in proving it, or you can just guess it, and that's good enough for me. But then this tells you that you have two eigenvalues. One is lambda equal to x plus q minus 1, and lambda equal to x minus 1, which is q degenerate, q times degenerate, q minus 1 times degenerate. Okay? Now, it turns out that out of these, the largest is this one, right? And therefore, if I want to compute the partition function z is going to be lambda plus to the power n, which is q minus 1 plus e to the beta j to the power n. And now you should get excited, hopefully, because you see that it's more or less the same of what we got.
Can I see the previous slide?
Yes. So you see that the free energy is exactly the same as the one we got before. So we were lucky enough. All right, so I'm essentially done for today. So next time we will see each other on Thursday, right? So Patrizia will hang out the problem on Thursday at 11. Can I shut down?
When will the session be start?
Patrizia is going to decide with her today, so she will tell me. She will probably send you an email. You know Silvia? Great, fantastic. Yeah, she's very good. You will see that she's fantastic. Okay, so she's going to start next week. I don't know when. Hopefully, because I cannot be here on Wednesday, maybe she will come on Wednesday. She will take my slot on Wednesday. We'll see. Oh, yay!